Alright, so welcome to Chapter 5. We'll spend today reviewing our laws of exponents. Some basic information. I will rewrite some of this a little bit larger for those of you sitting in the back. We've got x raised to the nth power. We call x our base. We call n the exponent. We call the whole thing, so the entire thing is called a power. That's what this says over off to the side here. The whole thing is called a power. Be a little neater about that. The first rule that we need to go over is the product rule. If you are multiplying two bases that are the same, so here my base is a, with different exponents, does anyone remember what we do with those exponents? Add them together. So this would be equal to the same base, a, raised to the m plus n power. We would add the exponents together. All right, our next rule. Oh, no, we're going to practice it first. Oh, no, we got our power rules. Sorry. All right, our power rules. I will write over them so we can see them a little better. This one, we've got a to the m power raised to the n power. Give me a minute and I'll rewrite it so we can see it. So we have a to the m power, then that in parentheses raised to the n power. So we are taking, we call it a power to a power, or raising an exponent to another exponent. Does anyone remember what we do with those? We multiply them. So that would be the same as the same base, a, raised to the m times n power. All right, the next one, we have a times b in parentheses, and the exponent on the outside of the parentheses is an n. For that one, that exponent can be applied to both the a and the b. So we would have a to the n power times b to the n power. The exponent outside the parentheses gets applied to each factor inside, being multiplied together. That is not the same as if we were to change this multiplication sign to an addition sign. It is not the same then. This is only if they're being multiplied like that. And that last one, it's just kind of mixing the first two together. So we have a to the m times b to the n, and the whole thing in parentheses is being raised to the p power. There can be. Oop. You can put one in there if you want to. A lot of the times in problems we won't see a multiplication dot written there. They'll just be next to each other like with other variables. You can always add the multiplication dots if it helps you remember what to do. So on this problem, we are going to take the exponent on the outside and apply it to each factor on the inside, each base. But when I apply it to each base, I end up multiplying it to the exponents they already have. So I have a to the m times p times my other base b, which is getting raised to the n times p. After product rules, we have quotient rules. So notice on these ones, we are dividing. That fraction bar means we're dividing. If we are dividing the same base with different exponents, what do we do? If we are dividing the same base, so both of these have a base of a, but they've got different exponents. We multiply them if we're taking a power raised to another power. Like on these ones, we're going to subtract. So we would have a to the, you take top exponent minus bottom exponent, m minus n. We'll see all of these in examples with other variables and numbers, not just all letters soon, so we can practice them. This middle one is similar to one of our product rules. If we've got two things in a quotient or in a fraction inside parentheses being raised to an exponent, both the top and the bottom can get that exponent. So this would be the same as a to the n divided by b to the n. You can apply the exponent to the numerator and the denominator. The very last one is going to mix some of our product rules with our quotient rules. So we are going to give the exponent outside the parentheses, that p, to both the numerator and the denominator. But because they already have exponents, we are going to have to multiply the exponent it already had to the new exponent that we're giving to it. So a to the m times p divided by b to the n times p. Okay, if we don't have any questions, are we ready to move on? All right. More rules. The negative exponent rule. If you have a base raised to a negative exponent, we make the exponent positive by moving it to the denominator. So remember, any variable, integer, anything, if it is not written as a fraction, we can write it as a fraction by putting it over what number? 1. A 1. So when we want to make this exponent positive, we take this whole thing and we move it into the denominator, or the bottom of a fraction. When we do that, in this case, the only thing that would be left in the numerator is a 1. That won't always be the case. Sometimes there will be other things in the numerator that will stay there. Never leave a negative exponent in your final answer. So anytime we're doing these problems, your answer should only have positive exponents. Never leave a negative exponent in a final answer. The zero exponent rule is my favorite one of all because it's the easiest and simplifies problems so much. If you have anything, any number, any variable, any expression, any set of parentheses, anything other than the number 0 itself, raised to the 0 power, it equals 1. The whole thing just comes out to equal a 1. So a could just be a variable, it could be some number, it could be a set of parentheses with a fraction inside of it. It doesn't matter. If it's getting raised to 0 power, it equals 1.
Even like a decimal?
Even a decimal. The only thing it wouldn't work on is the number 0 itself.
So if the exponent, well, the base is 0 to 0,
that is considered undefined. Yep. 0 to the 0 power is undefined. We won't deal with that in this class. It would not. We might be able to spend a day investigating that later on, but it comes out to be undefined. Well, we can talk about it briefly for now. So the rule is that anything raised to the 0 power is 1, but exponents tell us to do what operation? Multiply, right? Exponents tell us to multiply. And we learned a long, long time ago in elementary school that anything multiplied by 0 equals what? 0. So these two rules conflict with each other. Anything times 0 should be 0, but anything raised to the 0 power should be 1. They can't be both at the same time. So that is part of the reason why we say that 0 to the 0 power is undefined. But like I said, it's a little bit above of where we're going to go in this class. So we won't worry about it too much. Okay, let's do some examples. So we have all those rules. Now we're going to have to be able to apply them. I would make sure you're copying down the original problem and the answer, and maybe, just maybe even, like telling yourself which property you used or how you got to that example, or to that answer for the example.
No more names for the properties.
There were names for some of them. It's okay. You could draw arrows or number your properties if you want to be able to refer to them. You don't have to do that. It's just a study tip. All right. On example 1, we have the same base. The base is always x in this case, raised to different exponents, and we are multiplying the bases together. When we multiply the same base, what do we do with the exponents? Add them. So this would turn into x to the 2nd plus 4th plus 9th. So if you want to write out a little bit of work, 2 plus 4 plus 9, I heard several people saying that that is how they came up with x to the 15th power. So this is our answer, but if you want to write this middle step of how I came up with it, go for it.
So you wouldn't just be able to leave it like x plus 2 plus 4 plus 9?
Right, this would be considered a step or maybe showing work, but our final answer would be x to the 15th.
Okay.
Questions on that one?
So are all of the problems like that going to be like that, or the x is going to be numbers too?
We will probably get to ones where we'll have coefficients mixed in. All right, let's do another one. All right, in case it's a little hard to see, I rewrote the original problem with a white background so we can see it a little more clearly. So we are multiplying all of these sets of parentheses together. So I like to break it up and do it a little bit at a time. Multiplication is commutative, so I can multiply in any order that I want. First, I like to decide what sign, positive or negative, my answer will have. If I take a negative times a negative times a negative, will my answer come out positive or negative? Negative. So I know my answer will be negative. Then I've got a times a. There's not an a in the middle to multiply it to. That gets a little bit tricky. I know that if I multiply the same base, what do I do with my exponents? Add them. But I don't have an exponent written on either of these. Does anyone remember what exponent is implied if it's not written?
1.
A 1. So if you want, you can go through and put an exponent of 1 on any variable that does not have an exponent already.
So it will be negative a2.
So this would become a squared. If I take a to the first times a to the first, that becomes a squared, or a to the second. Yes, we still have our negative sign out in front of it. We're just building our answer a little bit at a time. Next, let's go on to the next letter would be B's. I have Good, we have a b squared times b to the first. We're still adding those exponents. That's how we get b to the third. Finally, we've got c squared and c squared. That gives us c to the fourth. So this would be our final answer. Notice we just did it a little piece at a time. Questions about it?
So did we only use the product rule on this and the negative?
We pretty much just use the product rule and the fact that multiplication is always commutative.
Are we going to write the rules and stuff?
You don't have to, it's just a suggestion if you want to brush up on your rules and write reminders to yourself later. Just a note-taking strategy.
What rule did you say?
This would mostly be the product rule and using the commutative property of multiplication. Just that we can multiply in whatever order we want to. All right, on this one, we are going to be using one of our product rules. We have technically two different bases inside our parentheses with an exponent on the outside. Our rule said that we can apply or give that exponent on the outside to every factor or base on the inside. So if you want, from the very beginning, you can separate the 2 and the x with a multiplication dot. That helps you remember. Those are two different bases or two different factors. So the first step, so to speak, of doing this would be to rewrite each base with the exponent. They didn't already have exponents written, so I know that they're ones, right? 1 times 3 is 3. So I gave the exponent to each base. But then I can simplify this a little bit. X to the third, we can't really simplify, right? We don't know what x is. But 2 to the third, that means I should take what times what times what? 2 times 2 times 2. And what would that give me? 8. So what this means is 2 times 2 times 2. That equals 8. I'm still multiplying it by x to the third. If you want, you can put your multiplication dot in there. You do not have to. Most of the time you won't see it there in a final answer. If we're multiplying the same base, we need to add our exponents. So when we start this off, I would rewrite the same base. My exponents that I'm adding are p plus 1. And then I would want to just simplify the expression that's in the exponent. What is p plus p?
P squared.
Careful, we're not doing p times p, just p plus p. 2p. So this would be 3 raised to the 2p plus 1 power. It does not get any simpler than that. We cannot combine 2p plus 1 because they are not like terms. We don't know what p is, so we can't take 3 and multiply it 2p plus 1 times. That wouldn't make a whole lot of sense for us to do. Questions or concerns on example 4? Okay, let's keep it going. Example 5, we're going to start pulling in our quotient rules. Goodness gracious. Safety plugs on these. Okay. Alright, we've got, well, technically we're applying a product rule and a quotient rule, but yes.
Is it 4 wild and 9 wild?
You're getting close. So We said that we can apply that exponent on the outside of the parentheses to the numerator and to the denominator. Okay, so I can give this squared to both the numerator and the denominator. But once I do that, then I can apply a product rule, because now in my numerator and in my denominator I have two bases inside parentheses with an exponent outside. So that means I can give that exponent to both bases. Same thing happens in the denominator. I've got two bases in parentheses with an exponent outside, so both bases can get the exponent. Then the last step is the step that Charles wanted to do. We actually apply what we know about exponents. So 2 squared is 2 times 2, that equals 4. The x squared stays there because we don't know what x is. And then 3 squared is 9. The y squared stays put. Okay, and then there's nothing else to simplify. 4 over 9 as a fraction does not reduce. X and y are different bases, so we cannot do anything to simplify them. So that would be our final answer. All right, on number 6, we are going to use another quotient rule. We are also going to simplify this like you would have done in elementary school, probably. If you have coefficients out in front of your variables, treat it like you would any other fraction. If I'm trying to simplify 25 over 5, what is that going to simplify to, Sadia? 5. So 25 over 5 just simplifies to 5. If I wanted to write it as a fraction, what would go in my denominator?
1.
A 1. In this case, we're not going to need a denominator, so I'm going to leave it alone. And then we have to simplify our base of x. If we're dividing the same base, what do I do with the exponents? All right. I heard a few different things. We subtract them. That's the thing I wanted to hear. Okay. We are dividing the same base, so we subtract the exponents. Divide the same base, subtract the exponents. We take the top exponent minus the bottom exponent.
10.
What is 15 minus 5?
10.
10. So this becomes 5x to the 10th. Questions before we continue? All right, we'll keep it moving. The next one gets a little more intense. Remember, the first thing we want to do is simplify the coefficients out in front like we would a fraction. What are both of those numbers, 35 and 56, divisible by? 7. What's 35 divided by 7? And 56 divided by 7 is 8. All right, so we did those. Then we have to move on to the x's. We're dividing the same base, so what do we do with the exponents? Subtract. We take top minus bottom, so 3 minus 5. Negative 2. For now, I'm going to write everything in the numerator when I do this. We'll talk about what happens in a minute later on. Okay, what about these y's? What are their exponents? They're both 1s.
So 2.
What do we do with the exponents? Subtract, so it becomes a 0. Y to the 0. Last, we've got the z's. What's the exponent on my z in the denominator? A 1. So we have 6 minus 1, that's z to the 5th. All right, now we're going to play should it stay or should it go. We know that the 5 and the 8 are staying where they're at. Now, the x squared, or sorry, x to the negative second, do we want that to stay where it is or move to the denominator?
Move to the denominator.
What happens when it moves?
It goes to positive.
Very good. If it goes to the other side, it switches signs. So now in the denominator, it's a positive x squared. What's going to happen with the y to the 0 power?
It's gonna stay.
That's a 1.
It turns into a 1, so it turns into like 5 times 1. Do I need to write that?
No.
No, multiplying by 1 doesn't change anything, so I can just kind of cross it out. What about z to the 5th? Should it stay or should it go?
Stay.
It stays. It has a positive exponent, and that's what we want. So there is our final answer. 5z to the 5th over 8x squared.
What rule did we use?
I'm going to erase these one at a time because I write big and I like to have a lot of space to do them. So I'll bring those back in just a minute. We're going to focus on number 8. The first thing I notice is that I have multiple bases in parentheses with an exponent outside. And that's the first thing that I want to deal with. So I know that this exponent outside can be given to each base inside. That means I would have 4 squared, and I would also have x cubed squared times. Over in this set, we would have 2 squared times x to the 4th squared. On our next step, we can do a couple things at once. We can just take 4 squared. What's 4 squared? 16. If we are taking x cubed squared, a power to a power, what do we do with those? Oh, I heard the right answer, but I also heard a wrong answer.
Add them. Multiply.
We multiply them. An exponent raised to an exponent, we multiply. Oop, sorry about that. That would be x to the 6th. Times, what is 2 squared?
4.
And again, we've got an exponent to an exponent. That becomes x to the 8th. But we're still not done. What's going to happen to the 16 and the 4? We multiply them together. 16 times 4.
53.
No.
Is it 48?
64.
It is 64. Now we are multiplying 2 of the same base. What do we do with their exponents? Add them. If we're multiplying the same base, we add the exponents. If we are dividing the same base, we subtract them. If we only have one base with 2 exponents, we multiply them. Lots of different things we got to keep straight. So 6 plus 8 gives me 14. Questions before I erase all that and bring back another problem?
That was the product rule, right?
That was a couple different product rules, yes. And the power rule. Power to a power. All right, let's bring back number 9. On number 9, what is the exponent outside of this first set of parentheses?
1.
A 1. So that's not changing. So you can just leave it as 5b for starters. Then we are going to have negative 2 cubed times c cubed times d cubed. Okay, that third power on the second set of parentheses gets given to every base inside that set of parentheses. Notice that I was careful to put my negative 2 in parentheses. We have to be careful when we apply exponents to negative numbers. So again, my 5b is not really going to change right now. Times, what is negative 2 to the third power? Negative 8. Is anything back here changing yet? Nope. So times c cubed times d cubed. What's the only other thing that can happen here? Multiply the 5 and the negative 8. What does that give us? Negative 40. When we do our variables, we usually like to go in alphabetical order. So b, c cubed, d cubed. If you want to put your multiplication dots in between all of that, you can, but you do not have to. That is our final answer. Again, none of these bases are the same, so they can't be simplified anymore. Any questions before we erase that and bring back number 10? Okay, then we'll erase it and bring back number 10. And I will get rid of some of our earlier problems to create some room. On number 10, I'm going to deal with my numerator and denominator separately. Make sure each of those is as simple as possible before I work with them together. And I'm going to kind of travel back up to the top of the slide to work. So this exponent outside the parentheses in my numerator, that is what I want to work with first. So I'm going to take 3 squared, x to the 4th squared, y cubed squared. Divided by, there's nothing to simplify in my denominator, no parentheses, no extra exponents, no bases that are the same. So it just stays 9x to the 8th, y to the 6th. Let's work on simplifying the numerator. What is 3 squared? 9. If I take x to the 4th to the 2nd, what am I doing with those exponents? Multiplying. That gives me x to the 8th. What about y cubed squared?
6.
Y to the 6th. Well, this is interesting.
Oh. He was 1.
Yes, so now we can apply our rules, or we can notice if you take something, anything, and divide it by itself, you always end up with a 1. Okay, so 9 divided by 9, that's going to give me a 1. Technically, what am I doing with these exponents for the same base?
You're canceling them out.
Sort of.
Subtract.
Subtracting them. 8 minus 8 gives me x to the 0. All right. Y to the 6 over y to the 6th. We do the same thing. We subtract those exponents. We get y to the 0. This step, you don't really have to write it out if you can see that they're going to cancel. Everything's just going to 1. That is our final answer, just the number 1. Our last example. There are multiple ways to approach this problem. You can make all your exponents positive first, and then work on applying your rules. You can apply the rules, then make your exponents positive after. I think that is the route I would like to go. All right. When we have the same base and we're dividing, what do we do with the exponents? Subtract. So I'm going to take negative 5 minus negative 4. Well, be careful with that. I'm taking negative 5 minus negative 4.
Oh, -1.
Negative 1. If we subtract a negative, we're really adding. For now, I'm going to put everything in the numerator. All right, we've got y to the 7th over y to the 8th. That also subtracts to give us a negative 1. And then the z, what's the power on the z?
1.
A positive 1. So right now, technically what's in my denominator is one big number 1. There are no variables in my denominator right now. But I'm not finished because I have negative exponents. So we got to play, should it stay or should it go?
Yep.
X to the negative first.
It has to go.
It has to go. Y to the negative first.
Has to go.
Also has to go. Z to the first.
It can stay.
It can stay. If you prefer to write your answer without exponents of 1, you can. It would just look like Z over XY instead of putting the 1s on all of them. Either of these is acceptable for a final answer. Is that a question?
Yeah.
Okay.
How do we know whether or not it has to go or not?
We want all of our exponents to be positive. So here, the ones that are negative have to move to the other side to become positive.